This section on chemical kinetics is on integrated rate laws for first and second order processes. Let's first look at an integrated rate law for a first order process. So a first order process is one as shown here where the rate is directly proportional to the concentration of A. Rate equals K times concentration of A. Using a little bit of calculus, which you don't need to know, if you rewrite the rate as a differential equation and then integrate to find the rate law for that first order, we get the natural log of the concentration of A at some point t, some time period t, divided by the concentration at time 0, so the initial concentration, is equal to minus K times t. So again, concentration of A 0 is the initial concentration of A, and concentration of A at t is the concentration of A at some time t during the course of the reaction. All right, so if I take that equation and do a little manipulation, if you recall, the natural log, when you divide a natural log, as you see here, that's the same as subtracting the natural log. So we have the natural log of the concentration of A at time t minus the natural log of concentration A at time 0 is equal to minus kt. And then I just added the natural log of A at time 0 to the right side of the equation to get the equation that you see here, where the natural log of A at time t is equal to minus kt plus the natural log of A at time 0. So what does this equation remind you of? Well, here's the really interesting thing. This looks a lot like a line. So this looks a whole lot like y equals mx plus b, where this is my y, t is my x, and the natural log of a0 is my b. So m, remember, the significance of m is the slope. So the slope is equal to minus k. Okay, so that means that for a first order reaction, how can we plot data to get a straight line? Well, we can plot this on the y-axis, the natural log of A at time t, and we can plot time on the x-axis. And again, what is the slope of the line? The slope is minus k. Natural log of A versus t will yield a straight line, and the slope of the line will be minus k.
Okay, so let's look at an example now of how we might use data to determine whether a process is first order, and then what we might do with that data. So let's consider the process in which methyl isonitrile is converted to acetonitrile, as shown by the reaction below. Data was collected for this reaction at 198.9 degrees Celsius, and then it was graphed. So currently on this graph we have pressure versus time. And we can see that we don't get a straight line. Also remember that graphing pressure with respect to time is the same as graphing the decrease in concentration versus time. And for a first order process, we don't get a straight line when we graph pressure versus time. However, if instead of pressure we graph the natural log of pressure as a function of time, a straight line results. So you can see here when we graph natural log of pressure versus time, we get a straight line with a negative slope as expected. And we can use that linear data, first of all, to recognize it as a first order process, but then also to interpret the data to find the value of k. So remember that the slope is equal to minus k. So we need to find the slope of this line in order to find the value of k and determine the units. So in order to find the slope, we need to just pick two data points on this line. So I chose this one at time 0 and this one at time 20,000 seconds. Remembering that slope is the change in y over the change in x. So just finding the difference in y on the top, so 5 minus 4 over The difference in x of the time when the natural log is 5 is 0, minus, we end at 20,000. Okay, so on the bottom we have units of seconds. On the top, natural log is a unitless number. And then in order to find k, I just need to flip the sign here. So I have a negative. And when I do that, I get that k is equal to 5 times 10 to the negative fifth, and this is 1 over seconds, or seconds to the minus 1. Alright, so there's the value of k and the units of k in one way that we can interpret data for a first order process given those integrated rate laws.
Okay, what about integrating rate laws for second order processes? So remember for a second order process that this is what a general rate law might look like, where the rate is proportional to the concentration squared. And if you do a little calculus, here's what you get for the integrated rate law. 1 over concentration of A at T equals KT plus 1 over concentration of A at time 0. And so again, we write this purposefully to look like the equation of a line, where this is my y. So a plot of 1 over AT. This is my x. That'll give me a straight line. And then, of course, 1 over A0 is the y-intercept. And the slope of the line is k. So we'd expect a positive slope there, different from a first order process. So a plot of 1 over concentration of A versus T will yield a straight line, and the slope of that line is k. All right, so look at an example of a second order process. The decomposition of NO2 at 300 degrees C is described by the equation below and yields data comparable to what you see in the table. So you have a sample set of data here from time 0 to time 300 seconds. Okay, so in the first graph, I plot the natural log of concentration, here concentration of NO2, versus time. So is this reaction first order with respect to NO2? And the answer is no. And why not? Because if it were, then this data would be a straight line. So this data here, natural log of NO2 here versus time, would be a straight line, okay? And so it's not first order because it's not linear. Okay, this data is not linear. However, if I plot 1 over concentration of NO2 versus time, I do get a straight line, okay? So is this reaction second order with respect to NO2? The answer is yes. And now we can find the slope of the line. The slope of the line is equal to k, right? The slope of the line is equal to k, so we can calculate k. Okay, so let's go ahead and calculate the slope of this line. So I'm just going to pick 2 data points, and I'm going to pick the first one at time 0 right here. I'm going to pick this one just a little further up here at 100 on the x-axis, 150 on the y-axis. So remember that slope is equal to k is equal to the change in y. So 150 minus 100, and that's let's see, the units there, 1 over concentration would be to the minus 1. And then the time, 100 minus 0 seconds. Okay, so a little algebra. Ooh, didn't mean to go quite so small there, sorry. 0.5 seconds to the minus 1. Molarity to the minus 1. Okay, so for a second order process, if you graph 1 over the concentration versus time, the slope of the line will be equal to k, and the units will be seconds to the minus 1, molarity to the minus 1.